Thank you. I didn't think anybody would want more, but you're here, so that's wonderful. So where are we? So I'm talking about the joy of dark matter in the narrow context of models from the lens of the production mechanism, sort of abstracting away the Lagrangian. So I didn't write many Lagrangians in the morning, and I'm going to continue with that approach, emphasizing the kind of cosmological history. And my goal is to give you the tools to do kind of back-of-the-envelope estimates so that a model builder who does have a Lagrangian can quickly assess at least which of the known mechanisms might be in there, and also ideally think about more mechanisms that are unknown using similar techniques. So I think that's the tools I hope that you can get from this, or at least a kind of way to connect these very disparate ideas into some framework for thinking about them. So yeah, sorry for this, but here I'm trying to sort of give a kind of classification scheme of different ways dark matter could be produced from the perspective of the mechanism, and there are some sort of discrete choices that enter the model and the cosmology that this flowchart is trying to emphasize. And this morning we talked about thermal models. So dark matter began with a thermal initial condition in kinetic and chemical equilibrium. And then there's sort of two categories, whether it does or does not have an asymmetry. And then for symmetric models, all of these are kind of universally cousins of the WIMP. That,
can you read what's in the parentheses below WIMP?
Sorry for my handwriting. Yeah, WIMP. Here I mean including co-annihilation and forbidden, okay. Just in the sense it's all the same diagram and the same Boltzmann equation. So I kind of put them all in one box. And kind of similarly, you could do that generalization to other boxes here. But okay, so all of these universally have the same sort of plot, and then what interaction decouples there is basically mapping to the box. But that can be exponentially important in terms of the couplings that you're looking for experimentally. So from the experimental point of view, this can be sort of desperately different, even though from this point of view, they're all kind of similar. And now I want to go more off the deep end into non-thermal models that are further from the WIMP this afternoon. So all of these models will be cases where dark matter is interacting too feebly so that it's not brought into equilibrium with the standard model thermal bath. This is less predictive, this side, because now it depends on the initial condition, whereas here the initial condition is thermal as a consequence of the interactions. Or a more positive way of saying it is the non-thermal side, maybe you can get more information about early times from the dark matter. So yeah, at least, so here I'm going to give a kind of quick review of this, and then I'm going to talk in some detail about this category and this, and I'm not going to discuss these, but for completeness, I want to put them there. And if you have a model that doesn't fit in one of these boxes, apologies. Or shout it out now, and I'll add a box.
Is this formal could be large enough to have cosmological influence itself?
Sorry?
If you have a lot of models, they would retain.
Oh yeah, eventually, yeah, indeed. Once you need enough bits for the chart, then the chart forms a black hole. Okay. But we're not there yet, but I'm hoping to give you tools to get us there. Yeah. Thank you. Okay. Yeah.
There's a limit of asymmetric where the abundance doesn't really have too much to do with the thermal behavior, right?
Yeah, you could. There's also non-thermal asymmetric. That's a good point. But then the fact that it's asymmetric, at least, so here, by the reason I put this thermal is in the kind of classic case, the assumption is the particle and any particle annihilate through thermal interactions. Sort of any of these, it could be asymmetric typically. So you can do asymmetric versions of a lot of these. But then the asymmetry is no longer what's setting the abundance in that case. Typically, it's sort of a parameter. It's sort of you can define it if it's a symmetry. If there's a notion of particle in any particle, then you might produce different numbers of particles in any particles. They might have never been brought into thermal equilibrium to annihilate. I don't know if that's what you're asking. But.
I was asking if there were other thermal scenarios where the abundance doesn't really depend too much on the thermal situation, except because the asymmetry can set the abundance.
Yes.
The thermal
yeah.
annihilation is working down.
Yeah, good. Sorry. So
So
I think it is kind of a special case from that point of view, to my knowledge.
all the other ones seem to depend a lot on.
Yes. There are other cases where the chemical potential can play an interesting dynamical role, and the asymmetry is captured by the chemical potential. So I think there is a wider space and interesting chemical potentials that one could talk about, but typically, I think this is kind of special. From the thermal point of view, it's a really initial condition, that you can then model through a genesis mechanism, and in that sense, it is distinct.
Yeah.
Thank you. Okay. Yeah.
Sorry, really dumb question. When people talk about gravitationally produced dark matter, where does that?
Yeah, I think that would be the production during inflation, at least the version I'm aware of. Yeah, and also inflaton decay or separate video. But I think they mean that. I mean, although permanent black hole evaporation would be another example of that. But I think when people say gravitational production, they normally mean this, to my knowledge.
Thank you.
And I'm not going to discuss that.
What about Wimp-Zillas?
Oh, yeah, I think that is an example of gravitational production.
Oh,
so that's an specific example of gravitation. Good. So my plan now is to give you a quick explanation of this, and then Anson will probably do it better next week, and then talk about these. These ones we can use similar kind of theoretical techniques to what we described this morning, thermal physics of sort of other states besides the dark matter. So it'll still be kind of Boltzmann equations and particles, which is what so that these are kind of the most similar to the thermal models. Yeah, whereas these ones are all quite different, and I'm not going to discuss. Okay. So I'm going to now erase this. Some of it. Okay. Yeah, so this one is really quite different. It's really production in the classical regime, which you can describe with classical field theory, because the dark matter is all produced, well, from the particle point of view, sort of at rest in large occupation numbers. And of course, this is kind of the original idea for making axion dark matter, although it's a more general idea than axions. It's sort of any gravitationally coupled bosonic degree of freedom can be produced this way. So as sort of a toy model for misalignment, I'm going to just consider the case where a mass term is dominating its potential. And I'm going to allow the mass to depend on temperature. This dependence is very important for the specific case of QCD axion. So I'll keep that so that we can map this general discussion onto QCD. And then, so dynamically, the important thing here will be the equation of motion in FRW. I'll leave the temperature dependence implicit. So in principle, one can just solve this equation given some initial condition. But I'll describe to you qualitatively what the solution looks like. So here's our potential. And we'll assume the field starts initially with some field value after inflation. Okay. Now, this equation has the behavior that if Hubble is much larger than the mass at a given temperature, then the field is frozen. This effect is called Hubble friction. And the field value is now set by this initial condition. And then the dynamics begins when Hubble crosses the mass, and then when Hubble is much smaller than the mass, the field will oscillate, and the energy containing that oscillation is the dark matter energy. Yeah.
Is that really pi squared?
Oh, did I? Thank you. Okay. Good. Okay. This can be solved using WKB approximation. And then the solution we can write like this. Yeah, we're allowing the mass to depend on time. There's dependence on temperature. And then we can write our initial condition. Kind of the convention would be to write this in terms of the cutoff that I'll call F, which is what we call in the axion context. And then this is just a dimensionless parameter that describes the scale where you start relative to the cutoff. Okay. So oscillations start at a temperature T star, which we can define to be when Hubble evaluated at T star is the mass value of T star, which I call M star. And the analog of the kind of sudden freeze-out approximation for WIMP, or the idea for sudden freeze-out is you call the energy density at the moment when it decouples equal to the final energy density, which neglects order 1 corrections that come from solving the Boltzmann equation. And analogously here, we can call the energy density contained in the axion oscillations the energy density at the moment when Hubble crosses the mass, and then that neglects order 1 effects that one can capture by solving this numerically. Okay, so this, because Hubble goes like in radiation domination, as we just reviewed, goes like T squared over on Planck. Here I just want to do back to the envelope version of this analysis. So neglecting G star and order 1 numbers, the temperature where oscillations start is the following. The energy density, this will be slowly varying after Hubble is far below the mass. And in that limit, the energy, we can neglect the derivative, and the energy density we can approximate just as kind of potential. Okay, and now the number of quanta is just, which I'll call it n phi, which is really the same number density we were talking about in the particle context, will be the energy density per mass. And finally, the dark matter abundance. We can use the same back of the envelope approach from this morning, namely, this would be the mass times the yield over temperature matter radiation equality up to an order 1 number. This is the mass in the universe today, so at sort of 0 temperature. And then this yield, we can approximate as the number of quanta at this moment when the oscillations begin. That's the kind of sudden approximation that I'm going to use here. That, like I said, is kind of the analog of sudden freeze-out in WIMP models. So let's just proceed. So the yield, as I defined this morning, is number density per entropy density. This is the thing that stays constant. Okay, and now we just want to plug in this expression evaluated at T star. Well, actually, before I do that, sorry. The entropy density goes like T cubed times an order 1 number, neglecting the G star. So let's write this. Okay, now I'm going to plug in the number density expression. Okay, and I get the following for the energy density. Okay, so this is kind of applying for generic misalignment. Where here I was purposefully agnostic about the functional form of the temperature dependence. The simplest case could be that it's constant with regard to temperature. The kind of nightmare type scenario I described earlier could be just a field like this that has no other interaction, just made gravitationally through misalignment. In the motivated case where this is the QCD axion, then QCD instantons predict a particular form for this temperature dependence, which then actually implies when the oscillations start, the mass is different than the mass at zero temperature. So in general, it's important to keep these factors. So let me just finally show you how to map QCD axion into this general misalignment expression. Okay, so what am I going to need? The mass, again, this is just back to the envelope level, goes as lambda QCD over FA, the mass at zero temperature. Instantons give a correction that suppresses this mass, like 1 over temperature to the 4th, at high temperatures. Okay, and now we have here T star is the following, and note that here we need to plug in this mass evaluated at T star. So there's a T star on both the left and right hand sides of this equation once you include the T star dependence of MA star. If I solve for MA star, then I get the following expression, which finally I can plug into here. And that gives me the following, including the famous 7-6 factor of F, where part of that is coming from this general form and part of it is coming from the F dependence of temperature dependent mass. Okay. Yeah.
Can you just remind me again how the temperature of the radiation quantity, how that sneaks into these expressions?
Oh, just that's the observed. You can think of that as a measure of the observed dark matter abundance. So for any model of dark matter, given that this is order 1 and that this is sort of is observed to be T equality, then I can write it this way. So that's just a statement of how much dark matter we observe. So here I'm matching this to observation, and then that tells me that m times y is observed to be EV set. Yeah, which I derived this morning, but that you could just set total radiation density equal to the dark matter density, and then that is true when m times y is of order T equality. Okay. Good. So, any questions about misalignment? I'm going to now pivot. Yeah.
Just, what's the value of T in for the axion case?
Oh, it's for all dark. This is observed for all models. It's 0.8 eV or 0.4. I had it this morning. 0.8. I forget my factor. 0.8 electron volts.
0.8 electron volts.
Yeah, that's just the lambda CDM extraction of the amount of dark matter.
Oh.
So that's, yeah, in that sense, it's equivalent to saying that omega h squared is 0.12 is equivalent to saying T equality is 0.8 eV.
Okay, thanks.
But I like to phrase things in terms of T equality so that you have the dimension full scale that you're aiming for in terms of the mass times the yield. Okay.
The temperature dependence of 1 over T to the 4th is pretty generic, or
this is for QCD, this is assuming a couple stage GG dual and then QCD instantons. I don't know, somebody, one of the experts, maybe comment if it's coupled to a SUN sector, how generic is it to report that? I don't know.
Depends on the number of quartz flavors. It ends up being related.
But as a free factor, power is less than 1. Yeah, I remember seeing different powers and some.
Yeah, because as quartz, as you start plugging in mass terms to the thermal instantons, you start tying up legs instead of letting them flow.
I see. So it depends on temperature relative to the quark masses in the standard model.
Yep.
Okay. And Anson will review this all much more coherently next week. So that this is an example of dark matter production that can be treated entirely within the realm of classical field theory. I mean, I talked about number of quanta just to kind of map to the way I parameterized the amount of dark matter this morning, but that really wasn't even needed. So this is an example of classical production. Another example can be interactions with cosmic strings in a bosonic field. This can also be treated using the realm of classical field theory. And the rest of this afternoon lecture, I'm going to talk about models where you really need the particle limit and more particle thermodynamics of the type that appears in the WIMP. Okay, but I do want to highlight an example of a classical dark matter calculation for you. Okay. So the kind of types of models that I'm going to now describe, people will sometimes refer to the whole category as FIMPs. The most famous example would be Friesen that I'll review. But before I describe Friesen, I want to make some general statements about this class of models that will apply to the different types that I'll describe. Okay, so for this discussion, dark matter is assumed to be kinetically decoupled at all times. So it is, therefore, it cannot be interacting much with us. Sort of with any thermalized bath particle, from which I'm writing schematically as phi, but including standard model particles, we're assuming that the rate of energy exchange for any process is much slower than Hubble. You can generalize a lot of what I'm saying to models with dark interactions that do themselves enter equilibrium, but for simplicity, I'm going to assume that for this discussion that the dark matter is kinetically decoupled entirely. Okay. And in this category of models, the abundance of dark matter is sensitive to its initial condition. Yeah, beautiful thing about thermal relic models is you remove any sensitivity to the initial condition. Thermalization washes out information about the initial condition. If the interactions are big, they drive the state into equilibrium, and you don't actually know what it looked like before. It removes information from that point of view. Here, that's not the case. So you do need to specify an initial condition to make a prediction, which makes these models less predictive, but sensitive to earlier times would be the more positive way of saying that. And the kind of common choice that's made, often without even saying it as an assumption, is zero initial abundance. So say, its initial condition, it's at its phase space distribution at first number density is 0, and then compute the buildup of abundance by some dynamics. If that's an assumption, in principle, you can append to any model a non-zero initial condition, like maybe the inflaton decays to some dark matter, and then dark matter is produced by something like Friesen or whatever. And really, in these models, you should add up all the production from different sources. So from that point of view, the different mechanisms I'm going to describe, they should all really be summed in a generic situation where multiple mechanisms are operating. Okay. But the kind of common assumption we'll make is that there is some process, a particle number changing process that produces dark matter. But in order to be consistent with this assumption, this process is producing dark matter slowly relative to Hubble. So that the dark matter is not brought into equilibrium by this interaction. Okay. Yeah, and then, so I'll describe now different examples, but the process could be a scattering process, where dark matter is in the final state. And the rest of these are something else. This could also be dark matter, but it doesn't matter. The assumption will be that these states are themselves in equilibrium. And then this becomes predictive in the sense that we can use equilibrium thermodynamics to compute the rate of this. But we assume that this rate is slow compared to Hubble so that it doesn't bring into equilibrium. And then if you make this assumption that you start small, and if it stays slow relative to Hubble, then you can neglect the reverse process. So that you can consider this in one way. And that will be true as long as you're far from reaching equilibrium. Okay. You can also consider decay. Or some other decays to dark matter, something else. Or we can consider oscillations between some state that's assumed to be in equilibrium and the dark matter. Yeah, so if it's scattering that's producing it, this is called freezing. If it's decay that's producing it, I'll actually describe to you two different regimes that are distinct. This can be another example of freezing. This can also be what's called Super-WIMP. I'll describe both of these in detail, but quickly the distinction is freezing is the production while the state is in equilibrium, and then this is the production after the state drops out of chemical equilibrium. And in general, those two contributions need to be summed. And it depends. The same model will have different phases where one or the other dominates. The famous example of this would be production of sterile neutrinos from active neutrinos. The generalization of that is something that I'm working on now that we call ROMPs for rapidly oscillating massive particles. Okay, and then one more thing that I'll describe to you would be exponential growth. Where if you do have some dark matter present initially, then you can consider 1 to 2, or in general, sort of n to larger than n processes. These can exponentially grow some initial amount to a larger amount, but still in the regime where this is not bringing it into equilibrium. Okay, so my plan for the rest is to describe sort of each of these cases. And in each of these cases, we can still use Boltzmann equation technology, similar to this morning, even though the dark matter is not in equilibrium, because its production is tied to other states that are themselves in equilibrium. Okay.
Is there a different phase when the other states are not in equilibrium?
I mean, yeah, you could also consider that. Yeah, I guess typically it would be if the other ones also start with small abundance, then nothing will happen. So you need something there, but indeed, if yeah, say something like you could freeze in. People, for example, have called sequential freeze in the case where you freeze in one state and then that state freezes in another state. So you can generalize to non-equilibrium initial states. Something needs to make them, which can be one of these mechanisms, and then you can do turtles if you want. But indeed, that becomes more complicated because at least if things are in equilibrium, then you know they're phase space distributions. So and here I'm gonna use the fact like that these states are in equilibrium. I know they're phase space. I maybe don't know this one's phase space, but the reverse process doesn't matter. If nothing is in equilibrium, then it becomes very complicated because
I think the question is more prosaic. Like, given that it's more complicated, is there any reason to believe that there'd be something phenomenologically different in that scenario, or you would just leave that as a complicated form?
Well, indeed, the interactions would be different, and I think it's worth studying more. But I don't know enough about that part of the model space to make general statements about it. But I think it's worth thinking about. Okay. Okay. So it's worth mentioning this is quite an old idea in the sense it's one of the classic ways gravitino dark matter is produced. You can also freeze in, say, dark radiation in the form of axions from similar interactions. People have studied, Kusenko studied stereo-neutrino production from freeze-in, but this 2009 paper by Hall, Jadamczyk, Marchoso West kind of named it and described it as a general framework, and that led to kind of a blossoming of ideas of models realizing this. So the name comes from this, but it was being studied in specific models earlier than that. So freeze-in will be an example of slow production versus Hubble, where it's assumed the initial states in the process are themselves in thermal equilibrium. And one can sort of generically consider some process that can even be agnostic about the number of particles involved, but there should be at least one dark matter in the final state. And this process is assumed to be slow enough that it's not bringing the dark matter into equilibrium. These states are assumed to be in equilibrium, and the dark matter is assumed to have a small enough abundance that we can neglect the reverse process. In that limit, in general, we can describe an integrated Boltzmann equation for the dark matter. Where we have a collision operator that describes all processes with dark matter in the final state, where we're integrating the matrix element squared over the initial and final state particles weighted by the initial particle phase-space distribution functions. And well, generically, since this is not bringing dark matter to equilibrium, the dark matter that's produced by these processes will not have an equilibrium phase-space distribution. So F is generically distorted. From equilibrium. However, at least in the examples that I've seen where the phase-space distribution is computed explicitly of this type, the distribution is kind of thermal-esque in the sense that it's a broad distribution with sort of order 1 occupation across different momentum modes. But if you wanted to precisely compute, say, the warm dark matter bounds from the free streaming length, you do need to model the phase-space distribution and compute the matter power spectrum from that. That has been done in specific models, for specific cases. So I'll give you just an example of Francesco D'Oramo and collaborators, for example, have been doing careful studies in this direction. So it's one of his papers. It's probably not the first to do it, but it's a recent good paper where they study the unintegrated Boltzmann equation and compute the phase-space distribution and look at the distortion. I'm not aware of anybody, including also the reverse process, but that ends up not being phenomenologically important anyway, but it would be much more complicated. So they're considering things in one direction.
Sorry, Josh.
Yeah.
If you start with some initial non-zero abundance for dark matter that is larger than what you would have gotten as the asymptotic value, still the reverse process would be negligible?
Well, the reverse process will be negligible in the limit where you're much smaller than the equilibrium abundance. But if you go
Too close to that.
but if it's bigger than this, then in general the reverse can be important. Yeah.
And what happens there?
Well, I'm not. Then you kind of. I'm not aware of any examples. Typically, you want a number density that's far below equilibrium to get to because in all these models, your mass is above a KeV because of Warm bounds, but you want your mass times yield to be EV. So the number density has to be, at the end of the day, very small compared to equilibrium. So to start with a number that's larger than equilibrium, you need to dilute it. Thermal models do that. So it's a model where you can successfully dilute a larger abundance without entering equilibrium. I'm not aware of an example like that. So in practice, normally the number densities are small compared to equilibrium. The reverse can be neglected, but maybe there are more general examples that could be worth thinking about. They would be complicated to calculate. Okay. So indeed, when computing this right-hand side, given the typical initial conditions one assumes, one can approximate that f is small, which is technically equivalent to saying that we can neglect contributions to the collision operator from reverse processes. Where you have dark matter in the initial state. And then, this is now not hard to deal with, then one can compute the collision operator using similar technology to a WIMP model. So let's consider this in general. Let me ask, at what temperature is dark matter produced? And let me specialize to 2-to-2 scattering for simplicity. And let's try to answer this question at the back of the envelope level. So let me call the initial state psi. I'm changing notation. This is whatever. So here this will be kind of like a WIMP, but we only need to consider one term on the right-hand side. If you remember from this morning, there's two terms for the forward and the reverse, but here we're neglecting the reverse. And this we can compute given the thermal initial state using standard techniques. Let's be agnostic for now about what type of operator is generating this. It's just so it's some operator with say the mass dimension d, and then now we can ask when is the dominant production, and this equation has the behavior that the dominant yield, the dominant comoving number density occurs when the rate, which is n psi equilibrium, sigma b per Hubble, is maximal. So let's just do the back of the envelope estimate of this. The amplitude will go like some energy scale over cutoff to d minus 4 if it's a dimension d operator. And now when we compute the thermally averaged cross-section, the relevant energy scale will be the temperature. So typically this will, we know the scaling with the cutoff, right, is 2d minus 4. Here I'm assuming that this operator squared is generating the relevant cross-section. And then by dimensional analysis, you can guess the numerator. This will typically be right. And then plugging this in here, if we assume this is relativistic, this goes like t cubed, Hubble goes like t squared over m Planck. So this quantity that determines production Okay, this is from psi, Hubble, 1 over Hubble. Here I'm neglecting G star and order 1 numbers. And then we plug in our cross section. Look at the following. So this comes from Hubble. This is the scaling we know, and then we'll get powers of temperature to get the units right. Okay. So this kind of scaling will dictate how a generic operator's production works. And then if you inspect the dependence on D, then we see that it's very important whether D is larger than 4 or not. And so we can kind of break this expression into 2 cases, which are called IR dominated, which is if D is less than or equal to 4, then the dominant production happens at low temperatures. And this expression, which of course diverges, but really here, right, I assumed T cubed, so I assumed this was relativistic. Once the temperature drops below the psi mass, when it's at equilibrium, that gets exponentially suppressed, which will shut this off. Or if it's lighter than the chi mass, then the thermal average will be exponentially suppressed. Either way, once you hit mass thresholds, you get an exponential suppression. So the production here will be dominated when you hit the IR mass thresholds that dictate the turn on of Boltzmann suppression. So dominant production will be at an infrared mass threshold. Let me define M to be the maximum of M psi and M chi, because whenever you hit the maximum, you'll hit an exponential suppression, in case there's a hierarchy between the two. So in fact, yeah, in the kind of 2009 paper where they named it Friesen, they defined Friesen to refer to this case of IR-dominated production. But people will kind of abuse the notation or often refer to also the higher dimensional operator case as Friesen, or sometimes people call it UV Friesen. But the other case, UV, if the dimension is greater than 4, then the production grows with temperature. So now it's UV sensitive. And then it'll grow until our description breaks down, which will happen at either when we hit the reheating temperature, which is the initial condition for a thermal universe, then the dominant production will be then, or if the temperature hits the cutoff and resolves the UV completion of the operator. Whichever of those scales you hit first will be where the production happens. So the dominant production, in this case, will typically be at the minimum of T reheat and the cutoff, depending on the ordering of those 2 scales. This is, for example, one of the classic ways gravitinos can be produced, where the operators are surpassed by the scale of supersymmetry breaking, or like axions, where you're suppressed by the F of the axion. But yeah, just to kind of be really clearly spell out the 2 orderings here, if T reheat, so we don't know what T reheat is, it's at least MEV scale for BBN, otherwise it's a parameter of the cosmology. If T reheat is less than the cutoff, then we can use the effective field theory during the entire evolution. And then sort of at T reheat is when the production will happen. If T reheat is larger than the cutoff, well then you resolve whatever generated your operator, which would typically lead to infrared Friesen at this scale, because we have some state coupled to the dark matter that itself is part of the thermal bath. Then the UV converts to IR production at scale lambda, and you have to specify the model. Okay. So, as a cartoon, let me just consider this one versus the IR. So if I'm plotting yield versus inverse temperature, here's our initial condition. Actually, we hit the IR. So the UV production, kind of will have it all happen right away. And people will sometimes kind of plug in like this Boltzmann equation with initial condition of T reheat, and then you'll just get that the yield is proportional to T reheat to an appropriate power. But really, if you want a precise prediction, you need to model the reheating dynamics, since that's where the production happened. Okay, and in the IR case, the dominant production will be sort of at the mass threshold here. For UV or IR. So like I said, the original freezing paper just calls this freezing. People often call this also freezing or UV freezing. Yeah.
I'm a little confused about TR larger than lambda case. Like, if I think about an EFD, in EFD mindset, like when I go to higher temperatures, like, I mean, that higher dimension operator is coming from some, I don't know, UV physics?
Yeah, now you need to specify the UV physics, and then that's part of the thermal bath, typically. So like, for example...
Can I think of that as an IR freezing, essentially?
So, yeah, exactly, that's what I'm saying. Yeah, this converts to IR. So, like, imagine that I have a 4 Fermi operator, like this. Then at temperatures, now my cutoff is this mass. At temperatures below that mass, the production grows with temperature. And now if the temperature reaches the Z prime mass, now the Z prime is part of the thermal bath, and then you can IR freeze in from the Z prime. Yeah, so that's what I mean when I say you resolve the UV completion. Yeah, and then typically it'll be an IR freeze in. That's a weakly coupled example, but anyway. Yeah. Okay. Yeah.
Is there any way you can imagine to observe the non-thermal nature of the kinetic distribution of the dark matter?
Yeah, that's a really interesting question. The only example that I'm aware of that I mentioned was kind of motivation of that reference I gave by Duramo is the phase-space distribution is an input to computing the cutoff in the matter power spectrum. So if you want a precision, say bound from Lyman alpha on the model, if you want to know is the bound 5 keV or 30 keV.
Near the warm dark matter
yeah.
limit, then you have.
Yeah, the warm dark matter limit is sensitive.
But if you're far from that limit,
then I'm not aware.
It's all very cold.
Yeah, there are models where freeze-in production can be tested in direct detection, like freeze-in of V plus minus through dark photon interaction can in some models give you large enough coupling to electrons to look for in some of these new ideas for direct detection, and then but then you're just sorry, that's just a halo distribution. Yeah, so sorry, I'm not aware of any example where you would probe it besides the warmth, but it would be interesting. Okay. Good. Okay. So let me actually do an example where I try to keep the factors of 2. Let me consider freeze-in from decay. Just to kind of give you an idea of a more sharp calculation. So in this case, the collision operator gives me the following expression. Yeah, where this is the thermal average of the decay rate. I'll tell you what that is in a second. Before we do carefully, let's just do an estimate. So the way of estimating freeze-in, well, for here this is decay. For scattering, the yield will be the scattering rate per Hubble evaluated at the dominant production temperature, which is either the IR or T reheat. For decay, it'll be the decay rate per Hubble. You can kind of guess these scalings by dimensional analysis, but they are right up to order 1 numbers. So in both evaluated at the production temperature, in this case would be the mother mass. So here then we can estimate that we'll get a decay rate, and the Hubble gives us m Planck over temperature squared, which would be temperature on the order of the mother mass. So this is the estimate. Now let me describe the order 1 numbers for fun. So thermally average decay rate means the following expression. These are factors of Lorentz invariant phase space. And importantly, there's a factor of the mother's phase space distribution function. And this, you can do this integral. I'll tell you the answer ends up being a ratio Bessel functions times the ordinary decay rate. This will be approximately the following at high temperatures, and recover the decay rate, the ordinary decay rate at low temperatures. Physically, this factor is just capturing the time dilation of the relativistic mothers. Okay, so anywho, it's convenient to work in terms of yield. It's sort of always convenient to do that. Here I'm going to define X in terms of the mother mass, not the dark matter mass, like this morning. You can rewrite the left-hand side in terms of yield. So changing variables becomes the following. There's this ugly function that ends up appearing when you change variables that captures the derivative of G star. But otherwise, it's kind of a nice simple expression. In practice, unless if there's a lot of degrees of freedom changing right at this moment, you can normally neglect this factor. The case where you cannot neglect this factor is if the decay is happening like during the era of the QCD phase transition, where G star is changing rapidly, then this factor affects the yield significantly. But if something dramatic is happening, then you can neglect that. So I'm going to take that limit. In the limit where I can, if I do need to include that, I'm going to have to proceed numerically. But if I can neglect that, then I can do the integral. We get the following expression, which indeed agrees with this back of the envelope intuition, and then that's the prefactor that appears. Yeah, in this limit where I can neglect G star's derivative. Okay, I'm going to make some comments if you really want to study these models. This is implemented in public codes like Micromegas that I mentioned earlier, which does thermorelics. It also does Friesen, so you can define a Lagrangian for this infrared case of Friesen. Then that code you can use. In Friesen models, just one warning, you do need to be more careful about thermal corrections from finite temperature field theory than you do in freeze out. So in thermal relic models, the production always happens when temperature is a factor of, say, 10 to 30 below the dark matter mass. And by that temperature, thermal corrections are not important. But in Friesen, you're always producing it on the order of an IR mass threshold. So like these psi's are at least semi-relativistic during the dominant production. And then thermal corrections, like finite temperature corrections to masses, can affect things. So precise predictions are actually quite subtle because of finite temperature field theory being complicated. Some of those effects are included in codes like Micromegas, but I think the kind of full there's even still some controversy maybe about exactly the full treatment and some limits. So let me just put that warning out in the air.
Switch to a discrete symmetry, like a Z2.
Yeah, there could be or not. Yeah, this model dependent. So I'm being agnostic here.
Well, I mean, if there isn't, then what is I stable?
Yeah, indeed. So simplest would be there is a Z2 and these are both.
And then what happens to psi and why? I mean, why isn't there a lot of psi left over?
The psi's are all decaying to chi's.
All the
Yeah, they all decay.
eventually all.
decay. But actually, we're going to come back to the size when I discuss Super-WIMP because there can be more production after they chemically couple. But yeah, simplest case would be that they share parity and all size decay to chi's. But because the interactions are so small in these models, it's not always lethal for the dark matter to be unstable. It ends up depending on the details, which is why I'm being agnostic here. So, but indeed, dark matter stability is always an important thing to check. Okay, but yeah, but it's not really that tied to the Friesen calculation in this case. Okay, good. So it's Friesen. Time. So let me give some quick comments about oscillations. What number went? Oh, 4. Yeah, I'll just advertise. I'll tell you about the kind of classic example of this, which is neutrinos, but we're kind of generalizing that in some ongoing work, and we call the generalization prompts. And this is ongoing work with David Dunsky and Sanya Hiba. But I'll tell you now, well, I'll focus to the kind of well-studied case of neutrinos in a second. But let me actually first phrase this in general. So here, this is kind of a two-step process. So here, the assumption is there's some state that oscillates into the dark matter. The dark matter is feebly interacting in the sense that it's never in equilibrium. The state that's oscillating into it is assumed to be in equilibrium due to some higher dimensional coupling with the standard model. So here my operator dimension is greater than 4. The classic example of this that I'll mention would be that these are active neutrinos. This is a sterile neutrino, and then this is called the Dawson-Widrow mechanism. So just advertise our ongoing work is to generalize that to more operators and particles, and then we call it ROM. Okay, but yeah, so there's some mass mixing in the flavor basis when I say oscillation. So there's some mass mixing here. And something I think is cool about this is it breaks the usual lore I described to you about how higher dimensions operators are UV sensitive, and you need marginal irrelevant interactions for IR production. Oscillations can actually regulate UV sensitivity of higher dimension operators in the following way. If we go back to our back of the envelope estimate, you now have to include this mixing angle, which depends on the temperature. This is the key point. This mixing will go sort of like this bare mass over, you can think of it as depending on the finite temperature mass of the thermalized state, which depends itself on temperature. And if we suppose, if we parameterize its temperature dependence by dropping with some power minus n, then this regulates the UV sensitivity as long as n is greater than or equal to d minus 4. Then this regulates the UV sensitivity. And generically, this will be satisfied. And then the dominant production occurs when this mixing is maximized. So the dominant production, let's define the temperature T off when the oscillations happen. And this will be where the kind of thermal mass is equal to the kind of larger of these masses, which is between the mass splitting. Okay. So this is our kind of general framing, which is work in progress. But now let me tell you the kind of classic example of this. Would be the Donaldson-Widrow mechanism, which is a paper from the early 90s. And the idea is to consider sterile neutrino dark matter produced from oscillations from active neutrinos, which are in thermal equilibrium. Of course, the active neutrinos are in thermal equilibrium due to weak interactions, like 4 Fermi operators that, as I'll describe, the production occurs in the regime where we can integrate out the weak interactions, so it's a higher dimension operator. Right, and naively, you would think, well, like this plus this should grow with temperature, because this is growing with temperature within the EFT, but the medium effect shut off this mixing in a way that regulates that UV sensitivity is what they observed. Yeah, so we'll have operators like this, and of course quarks and yada yada. So the scattering is dominantly dimension 6. The medium correction to the mass, something interesting happens. The dimension 6 pieces vanish in the limit. They end up going like number of, say, electrons minus positrons. So in the limit of a symmetric plasma, the dimension 6 contributions of this vanish. It's not obvious, but that's true. So you're actually dominated by dimension 8 operators. Like, for example, operators coming from the next term from the W propagator, where you have derivatives. Operators like this end up dominating the thermal active neutrino masses. This generates correction to mass that goes like this, which means the mixing angle goes to T to minus 6, which is far more suppression than you would have needed to shut this off. So that's why you can compute the sterile neutrino production within the realm where you integrate out the weak interactions. Yes, what is the oscillation temperature? That is when this correction to the active masses is on the order of the sterile neutrino mass. Which would be the following, which turns out to be kind of around the 100 MeV scale if the sterile neutrino mass is around a keV. And that's sort of the mass scale where sterile neutrinos have to live, because if they're too heavy, they decay too rapidly. Which makes them kind of interesting from the point of view of warm dark matter. But anyway, you actually coincidentally have the dominant production from the oscillations in this model around the epoch of the QCD phase transition, but really that's coming just from this geometric mean of the bare mass of the sterile and the medium correction to the actives, which is coming in this case from a dimension 8 operator. This is no longer a viable model actually for sterile neutrino dark matter in the sense that you predict the X-ray line that you're getting at one loop. And now extra observations exclude the sort of size of the mixing angle where this would give you the observed abundance. So it seems no longer to be viable, but at least it was back in the early 90s, and just advertised we have ongoing work generalizing this to the case where this is no longer assumed to be an active neutrino, and the operator can be generalized too.
The mass eigenstates you get from psi and chi, do they both have to be a stable?
Well, so at least one of them is decaying the other. So that's why stereo neutrino dark matter is unstable. Okay. It decays to active, but it can be stable enough if it has a KEV scale for the sort of mixing angles of interest in this case. In the generalized case, the heavier one of the two will decay to the lighter, and you could consider either mass ordering. So you could.
Okay, so the dark matter is stabilized, but kinematically, essentially.
In the case where it's lighter than psi, as for sterile, but in the generalized case, you can now take the dark matter to be the lighter of the two, and then it can be exactly stable.
I mean, you said it's going to be something that is in the standard. Psi has to be in the standard model.
No. Oh, sorry, psi is in thermal equilibrium with the standard model. For Dalton-Withrow, it's an active neutrino. In general, you can relax.
It has to be a singlet of a standard model gauge groups because it's oscillating with dark matter, right?
Yeah. It better be a singlet of QCD and QED.
Oh, okay.
Okay. Two more. So, next, second to last will be Super-WIMP.
Sorry, maybe just a nice question.
Yeah.
So oscillation, so oscillation is an example of a relevant operator. If I did, like, let's say a decay, I would still have the same feature, but that would regulate the UV sensitivity. Is it correct to say that you have one irrelevant and one relevant, and that's why you're getting a...
And the key thing, I think it's really mixing that's special in this case. So I don't think decay can. But maybe I need to think about it. Typically, if it's decay that's generated by a high dimension operator, that operator also generates scattering that's UV sensitive. But yeah, you're asking are there more general cases where you can regulate, and I'm not aware of that, but discuss that.
So can kinetic mixing of photons and dark photons fall into this frame?
Yeah, good question. Yes, and that used to be viable, and there were papers studying that, and it's now excluded experimentally by direct detection experiments that would absorb the dark photon. So that like 15 years ago or 10 years ago was viable, or I forget exactly, but now it's not. Yeah, it was studied, for example, by Maxime Pascal. But yeah, so indeed, a photon mixing with a dark photon, you can sort of freeze in or oscillate in to the dark photon, but then that dark photon that predicts a particular absorption rate in direct detection that now excludes it. Yeah, so the dark photon case is now experimentally excluded, and it used to be. The sterile active case is also experimentally excluded, unless if you add large lepton asymmetries, which then make this generated at dimension 6. That's called Schiefler mechanism. So there's still a window for steriles with a large lepton asymmetry. And then and then you can generalize it to not being a standard model particle, and of course then there's a much broader space of possibilities. Okay. Good. Any more questions on oscillation? Just a technical comment before I move. The oscillations also allow for quantum effects that are not captured by Boltzmann equations, like coherent resonances, things like Landau-Zenner resonances. Those are not captured by Boltzmann equations. There's a generalization of the Boltzmann equation called the quantum kinetic equation that's been applied to neutrinos that can be applied in this case. So basically, oscillations can be either resonant or non-resonant. It turns out Dalton-Withrow can be treated with the Boltzmann equation, but then there are other cases that can't. And then you do need more machinery. So I'm just going to mention that as a technical aside. So this is also a way gravitinos can be made, so it also has a long history. This particular name is due to Jonathan Fang, Ruderman Takayama. And sometimes a more descriptive name will be given. Freeze out and decay. And this is also the idea of considering production from decays, but for the freeze-in, that means the mother is in thermal equilibrium, and then the dominant production is when the temperature is on the order of her mass. Whereas here we consider production after chemical decoupling, so there's sort of two steps. Cosmologically, the mother, I'll call psi, freezes out. So maybe it's like approximately stable through Z2, maybe it annihilates. The classic realization of this would be that it's just particle, or like maybe an NLSP, and then the dark matter can be the gravitino in kind of old versions. So step one, psi freezes out. Step two, psi decays to the dark matter. So this is captured by some cross-section. This is captured by decay. So if I make a plot of the thermal history here, I call x sine t. This yields. So first let me draw psi. So psi will go through kind of a WIMP-like freeze-out. So let's call this moment x freeze-out, which is when n psi signifies Hubble. And then at some later moment, decays. Let's call this x decay. There will be, so chi will have some initially always some production from freeze-in, here, but then in the regime where this is dominating, you then get a later production there. So you make chi. So all the psi become chi. This time is defined to be when the psi decay rate is. So we're assuming that's well separated from this moment. So again, the freeze-in production is when the psi's were still in thermal equilibrium. Actually, I drew this too soon. Sorry, because this really should have been. Okay, let me call this. This will be dominated when this is of order 1. Okay. That's a more realistic version. Okay. So before decay, so let me call the following the abundance that psi would have if it were stable, and then we can just use our WIMP result. Okay, just like the WIMP, but then it decays, and then it's very simple to analyze because it's just that every psi decays to a chi. So the final yield of chi is just the yield of psi from freeze out in the limit where this dominated. And this means, so that we'll make chi, bring us that freeze out, which by definition is this, but these are equal. So the abundance of chi is just given by the ratio of the masses. So you suppress the abundance of psi by the ratio of their masses. So really you want to consider a part of the model space where the size, if they were the dark matter, would be overclosing is too much. But then when they decay, you dilute the energy density by the ratio of the masses. And then you can, so then you can just plug this expression here. Psi. So this quantity should now be order 1. Okay. And indeed, as I was emphasizing here, again, this type of model will have production both of the Friesen type that I defined for you before and the Super-WIMP type. And you need to add them. And in practice, it depends on where you are in the model space, which of those two dominates. So you can think of that as different phases. Indeed, in the supersymmetric example, there are parts of SUSY parameter space where you make more gravitinos from Friesen. There are parts where you make more gravitinos from the decay of superpartners after they froze out. So you can think of those as different phases of models.
Why did you say add them? Because in that plot it looks like...
We'll add them in the sense, every psi becomes a chi.
But is that, the chi line is in the same level as...
It's a log.
Yeah, sorry. Yeah, it's a log plot. Thank you. Yeah, so really, thank you.
Okay, gotcha.
Yeah, so, yeah. Add them, yeah. Yeah, so y chi. It's kind of y chi Friesen that you would compute using the math that I described before, plus y chi. Yeah, that's there. Thanks. Okay, good. 9 minutes. Which is perfect. This last one's definitely not worth more than 10 minutes. Okay, so the last case I'll discuss was sort of something kind of in between. It's still going to be feebly interacting, but unlike all the ones I just described, all the models I described so far in this lecture, the production is independent of any prior existing population, which is why I was saying you should add them. Sort of they enter additively. An exception to that is if the process relies on dark matter in the initial state. Then you can get exponential growth of whatever initial abundance is present. So the idea here is we assume that chi starts far below equilibrium abundance so that we can neglect the reverse process. This state is assumed to be in equilibrium. Well, you could generalize it to where it's not, but let's make that assumption. This state's in equilibrium. This is not. But then this process takes 1 and makes 2, 2 to 4, and so that gives you exponential growth of whatever initial condition is present. So here, this can be described by the following integrated Boltzmann equation. Yeah, and I'm neglecting the reverse process because I'm assuming that n chi is much smaller than its equilibrium abundance. Unlike the other Fint models, this now depends on the initial condition. This could be, well, just a really initial, like generated by inflaton decay, or it could be generated by one of the mechanisms I just described, like maybe you freeze in a little bit, but it's underabundant, and then you grow it through this process. So this equation, if you go to field space, can be solved simply. Yeah, we're here. Okay. And so the exponential growth begins when this approaches order 1. So if you consider the case where this process is generated by a marginal irrelevant operator so that it's IR dominated, then you can have the initial condition be safely far from equilibrium. And then this process suddenly starts to matter. The chi is sort of trying to enter equilibrium at that stage. And if you allow this to continue, it'll just thermalize. So that, and that would be too much dark matter. But you can disrupt that. Yeah, so you just say the exponential growth begins. When this becomes order 1, which you can arrange to happen in the infrared if this is generated by some operators with mass dimension less than before, by the kind of general discussion we had before. So if the exponential growth occurs unchecked, then psi will thermalize. Which you could consider, but to make it dark matter, you want to stop that. The exponential growth stops. At an IR mass threshold. Which will be whichever of these masses is heavier. So you can arrange with chi. There's some initial amount. And then you have exponential growth. And then you can stop it. I mean, it will stop if you hit whichever mass is heavier. So as long as, so if the exponential growth begins like the correct number of e-folds before the mass threshold, then that can grow it to the observed abundance, but it does need for the scales to be correct. Okay. Let's see, I still have 2 minutes. I can just.
Having an initial condition.
This process, since this is in equilibrium, there will be some irreducible amount of freezan. So I could use this twice. So for example, that could be the initial condition, would be freezan. We also have an explicit model where we do this for stereo neutrinos, where if stereo neutrinos are self-interacting, then you can mix once, and then you can have exponential growth from sterile scattering active neutrinos, and then the initial abundance can be just Dodelson-Ridgerow oscillations, as an example, which are underabundant in the allowed parameter space. So you can take some initial, so around QCD phase transition, some active neutrinos oscillate to sterols, there's not enough of them to be dark matter, but then they can exponentially grow the observed amount. That's, I think, the nicest realization of this. Okay. So I'm out of time. I probably should end with some sort of positive, forward-looking summary comments, but we're out of time. But that's, so I've tried to give you an overview of the landscape of some mostly recent ideas for how dark matter could be produced beyond the WIMP and the axion. I do honestly still think the old ideas are the best, but they might not be right, so we should try to understand the theory space. Each of these models can have many realizations. The experimental prospects tend to be very different than those classic examples, and one could have a lot of discussions about the experimental tests, and some of these models can be very hard. And please add your own boxes to the flowchart as you will.
was in the darkness.
I told you.
I mean, from the perspective of say, theory guiding experiment, is the takeaway from the proliferation of models anything goes?
Yeah, maybe. Not anything. We only have one number, the energy density. There are a lot of ways to map into it. So yeah, indeed, it's not that we can't explain it. We can explain it too many ways. But one I think lesson, even just in the thermal models, like really small changes in the theoretical structure can lead to exponential excursions in the parameter space. So the experimental prospects are very sensitive to these assumptions, whether we like it or not. Yeah, sorry, you want me to say something more optimistic, but that is I take away that if you have sort of a generic sector with multiple massive states with generic interactions, then depending on moving the masses past each other and which interaction dominates can lead to an parametrically exponentially different coupling that gives the observed abundance. So the mapping between the experimental parameters and the abundance depends on these assumptions.
I mean, that's of course the nice conclusions for say the AI people who tell us that AI will do our jobs because the issue is not coming from theoretical models, it's data. So that's good.
Yeah, we need the data.
All right, well, let's thank him again.